Hello, everyone. My name is Beth Capellas, and I'm the Sales and Support Manager here at Triangle Microworks. I'd like to welcome everyone to our latest webinar, Charting a Course to a Digital Substation, How to Integrate IEC 62850 in Your Existing Solutions. This is a three-part series, and part one was hosted on April 13th. If you missed it, you can find the recording at our website at trianglemicroworks.com. You do not have to have seen part one to understand part two. They are related, but can certainly stand on their own. Today's webinar, part two, is focused on IEC 62850, SEL, and the engineering process. We'll talk a little bit about part three, which is focused on strategies for integration of DNP3 and IEC 62850 a little bit later in the webinar. However, you can always find out more details on our website, again, trianglemicroworks.com, under the training tab. So before we get started, I'd like to go over some housekeeping items while everyone is still joining. The webinar is scheduled to be 1 hour long. We have a lot of material to cover today, but I will try to take at least 1 to 2 breaks to answer questions. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit your questions as soon as you have them. Please don't wait until the end. We will begin answering questions online as we have several engineers monitoring the questions and responding to them directly. We are also happy to stay on after the webinar is over and answer as many questions as we can. But your best way to get an answer is to just submit the question as soon as you have it. So with that, I'd like to introduce the folks behind the scenes answering the questions. Today we have with us Dave Galkenauer, Lead Developer for Distributed Test Manager, DTM, one of the tools that you'll be seeing here today. We have Phil Young, Lead Developer for Triangle's IEC 62850 source code library. Eric Fabre, our Senior QA Tester here at Triangle, and Andy Reuter from Helix. Next, I'd like to introduce our speakers. First, we have with us Christoph Brunner, President of IT for Power. Christoph is a well-known utility industry professional and a 62850 expert with over 30 years of industry experience. Christoph has been involved in the development of the standard since the beginning. He is convener of Working Group 10 and member of Working Group 17, 18, and 19 of IEC TC57. He is an IEEE fellow and a member of several IEEE working groups, as well as a member of the PSRC main committee and the subcommittee H. Next, we have Jackson Moore, application engineer at Triangle Microworks. Jackson received Bachelor's of Science degrees in both electrical engineering and computer engineering from North Carolina State University, and has a background in power system engineering. Prior to joining Triangle Microworks, Jackson spent 5 years as a microgrid system engineer where he designed and developed load management control systems for multi-source microgrids, ranging from 1 megawatt to 30 megawatts. In his current role of application engineer, Jackson serves as a bridge between our customers and our development team, seeking to understand and solve the unique and complex challenges that our clients face today. So now that you know everyone, I'd like to give you a little bit of background on Triangle Microworks. We were established in 1994 and have over 28 years of communication protocol experience. We are headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and generally reduces their costs and development time. Licensing a source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field. They are designed to troubleshoot, to simulate, and automate testing for both a single device or a complete substation. Lastly, we also provide a SCADA data gateway, supported on both Linux and Windows, for protocol translation and data concentration with standard SCADA protocols as well as OPC. It's available as software only or pre-installed on hardware. We are heavily involved in the standard committees that support SCADA protocols, like UCA Group for 61850 and DNP user and technical committees. Through our participation, we help define the protocols, stay up to date on changes taking place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I would like to go ahead and hand it over to Christoph to kick off our webinar. Christoph, I'll go ahead and make you presenter.
Thank you, Beth. Welcome everybody from my side. Okay, so in the first part of this webinar series, we compared IEC 61850 with DNP3, and we explained some of the concepts of IEC 61850 related to communication and to modeling of application data. As part of that, we also have compared the DNP3 XML file with the IED related files of the IEC 61850 system configuration language, or shortly called SCL. The files are used as part of the engineering process described in IEC 61850-6. They can describe a template of an IED, the ICD file, or an instance of an IED. In the case of an instance, the file contains already some specific configuration information for the system in which it will be deployed, like ID name or communication parameters. The engineering process with IEC 61850 will be the focus of today's webinar. We will start to introduce the process as it is supported today. At the end of the webinar, we will provide a little preview on some future developments regarding this engineering process. The process starts with the specification, which supports the machine processable description of the substation topology, basically the one-line diagram, and the specification of the data model to support the required functionality. As part of the design, then when we start with the implementation, IEDs need to be selected, functions need to be allocated to them. Then we need to do communication engineering for the IEDs, and the signal flow required for the application needs to be translated in GOOSE and sample value messaging, as well as in reporting. Finally, the functions need to be implemented in the IEDs, which may include some logic configuration and signal binding. During the process, in the edition as published today, we basically have file support in SCL. When we finish the specification, we can export what we call a system specification description, which can then be used by the system configuration tool together with the ID capability description that we get from the vendor tools to start the design. The whole design is then done using the system configuration tool. When we do a top-down process, at the end we can export what we call the system configuration description file, which contains all IEC 61850 aspects of the system design. This is then used by the IED tools to finally configure the devices and create final configuration of the devices. We will now go step by step through these different stages and discuss them in a little bit more details. And we will start with the specification. As already mentioned today, when we talk about specification in the SCL or system configuration language, this mainly includes the one-line or single-line diagram, where we have a hierarchy behind, where the substation is hierarchically divided into the voltage levels. Under the voltage level, we have the base, and within the base, we have the conducting equipment like circuit breakers, switches, or instrument transformers, as well as the description how those are physically connected to each other. The second part that we can put in the specification is adding the functional requirements in terms of having the logical nodes representing the functional elements that we want, as well as to add the signals that we require from the logical nodes. When we compare that to a conventional approach without the IEC 61850, when we do a specification, the functional requirements is mainly done in a textual document. What we can do is to have a signal list as well that can be specified, the signal list of the signals typically that we want to send to a gateway, to the SCADA system. and the single line diagram is provided as a drawing. In the case of 6150 using SCL now, as mentioned, we can do some of these parts in a machine processable way. And the result is basically of this first step that we introduce in an SCL file of the type SSD file, that we add there what we call the substation section, which is more or less containing the requirements and the substation topology. So that's the first step. Now let's have a look how this looks in praxis. So before we show that on an example, I would like to introduce you an example that we will use in today's webinar along the engineering process to show you how the different steps are working. So the little application that we have chosen is a substation with 4 feeders. We have 2 line feeders getting into the substation, and then we have 2 transformer bays where we go to the lower voltage side, and we also have a measurement bay. We assume that we have a solution with a process bus. So we have per bay, we assume we have 4 devices. Besides the bay controller and the protection device, we also assume we have a merging unit that is getting us the samples of current and voltages, and we have a switch control unit which provides the interface to the switch gear. From the functional requirements in our little application for the line feeders, we assume we have distance protection with 2 zones, a distance protection scheme, line differential protection, breaker failure, reclosing, and synchro check. And for the transformer base, we have differential protection as well. We assume we have a differential busbar protection additionally. As a little reminder on the IEC 61850 data model that we discussed last time, that's an extract of the data model that we use for our application. So here we see the 61850 model for some of the different functions and signals. Here we would see how this would look when we would model it in DNP, the different kind of data that we would have as DNP points. So as an example, our breaker interface, where we get the position of the breaker from, the breaker interface in 61850 as a function element has the logic node XCBR. The data object of the position where we find the position information will be xcbr.pos.stval. And in DNP, this would basically be a double bit input with a certain index number. Similar way, our protection functions, protection elements, measurement, just as a few examples, but we'll see them now as well when we look at the example. So that's the little task that we want to do today. We want to design, specify, and then design that little substation. Now, how do we do the specification? Specification can be done with a system specification tool. And here I show a few screenshots how this would look. Later on, Jackson will demo the tool as well in reality. So we are using the Helix STS, which is both a 61850 system specification as well as a system configuration tool. The first step when we start to create a project is typically to enter the single line diagram. So we design more or less our application, the single line diagram, in the model of 61850. So behind the complete 61850 model is built up to describe this single line diagram. In the next step, then we can enter into the different bays and provide the specification of the functions and signals that we are requiring. So as an example here, we have functions like interfaces to the switches, interfaces to the breakers, the current and voltage transformer measurements. We have our protection functions over here, the different elements of the protection functions, protection related things like breaker failure, reclosing, synchro check with the corresponding 61850 logical nodes, as well as the control of the breakers and switches. What we also can do at that stage already is to allocate that to virtual IEDs, so to express the requirements, how we think we would like to have these functions later on allocated to devices. So as an example, current voltage transformers here associated to a merging unit. We also can define signals that we require. So we took an example here of the XCBR, so we can provide in detail the signals that we require for our application from a XCBR, and we express that from the data model of IEC 61850. Behind, when we do that, the tool will build up the SCL model of this substation structure, and that could basically look like this. I show here the hierarchical view. Behind that, we will have an XML file according to the schema in 61850-6. But here we see the hierarchical view, substation, voltage level, base, and in the base, the conducting equipment. And at different levels, we can associate the logical nodes that express our functional requirements. So that was the specification stage. Next stage is now IED selection and import of the IED into the system tool. So basically, we can also call that IED pre-engineering. So in this stage, we get from the device manufacturer the IED capability description, which contains communication and engineering capabilities of the IED, as well as the data model according to the functionality. This corresponds, as already mentioned, basically to the DNP XML file that we have when we will do a DNP3 project. The ICD file can be available for a product version depending on the functionality, but it can also be customized using the IED tool by selecting the required functions if you don't really need the complete functionality that is supported by the device. The model that we have behind, when we look at an IED, we basically have an IED that includes servers. An IED has an access point where we have the communication access. And in our SCL model, that's modeled as a hierarchy where we have the IED with the access point. We also have a section that defines the services, which defines the capabilities. We will see that later in an example. Under the access point, we have our server that then provides the complete data model of the IED. So basically, when we look at our SCL files, the system configuration language files, what we have in this stage is what we call an IED section, which is called template at this stage because the IED is not yet an instance, but from an SCL file, we have one element in that we call the IED section. And with that, I would like to hand over to Jackson to give a little demo and a practical example of an ICD file.
Okay, Jackson, you should have the screen.
All right, thank you, Christoph, and thank you, Beth. So as Christoph mentioned, one of the important stages of the engineering process is compiling your different IED capability descriptions, or ICDs, which is what you see up on my screen now. And I'm viewing this with our tool SCL Navigator, which is an application for creating, viewing, editing, and verifying 61850 system configuration language files, or SCL files, and also as a built-in intelligent editor. So just to familiarize yourself with a couple of the different parts of an ICD. Up here at the top, we have just some version information, and this is going to be dependent upon the vendor who comes up with this capability description and then provides it to you for integration into your project. Moving down, we see the header section, where it's just an editing history. We can see the different changes that were made by the vendor when they created this IED capability description. Below that, we see the communication section, and Christoph is going to talk a little bit about this in the next step of the engineering process. But at this stage, because this ICD has not yet been instantiated or associated with a specific device, the communication section is going to be pretty empty and might just have some basic default values. The next step below is the IED section, which is where we start to get into the meat. And contained within that are two parts, the services section as well as the access points. So the service section is where we really get to see the capabilities of this IED. So 61850 is a large standard, and there's many different parts or features that could be supported in an individual IED. So when a vendor or manufacturer makes an actual IED and they want to document what its capabilities are, they can do that here by listing what services are supported. So for example, we could take a look at line 37, where we would see the GOOSE attribute. So this would indicate that this device is in fact capable of GOOSE and that it can support 10 concurrent GOOSE streams. That'll be useful when we import this ICD into our system configuration tool. To take a look at another one, we could look at line 41, the configuration for signal references. And here we see the number of, for example, GOOSE streams that our device can subscribe to. So in summary, the combination of all of these things are the documentation of what my device is capable of. And it's in a machine readable format, which we can import into our system configuration tool. Below that, we have our access point. And within that, we have the different servers that are on our device. In this case, as is common, we have a single server, but that's not necessarily always the case on our single IED. And then within that, we have different logical devices. In this case, we have a protection logical device and then actually a backup or secondary protection logical device. But you could break up control and protection or other different functionalities that your device performs into different logical devices, even though it's all on the same single box. And again, this would be done by the manufacturer. It's just a bucket to place your functions or applications in. Within that, we see different logical nodes. And this is kind of what 62850 is famous for, the hierarchical data model that's browsable, as well as logical nodes. Logical nodes, as Christoph mentioned, being different buckets to hold data associated with a given functionality that our device is performing. For example, we see this RBRF down here. So that's a logical node class, and it is associated with breaker failure. So any data attributes that are associated with the breaker failure functionality of my device might be held within this logical node. Another one would be the PDIF. So that's going to be a protection indicated by the P leading and then diff for differential. But you'll notice that I cannot expand these logical nodes further to see what data is inside of them. And that's because it's defined down in the data template section. If there was multiple implementations of a single logical node, like I see up here with my LGOS, then I would only have to define the template for it once. So if I right click on, let's say, my RBRF in the tool, I can use the navigate to feature and go down to the template. Down here, the template, I can expand out and see the different data objects which make up this logical node. And then if I want to take one of those, for example, the OpX would be an operate external DO, I can right click on that. DOs themselves can be made up of more DOs or data attributes. In this case, I can right click navigate to and find that individual DO and see the different data attributes which make it up. So in this case, I would have a general. So as we'll see here in a little bit, once we navigate to some of the other tools, this whole path that I went down through the navigate to features, that's going to make up a whole path to a data attribute, starting with our IED that we saw up at the top, moving down into our logical device, and then our logical node, for example, the RBRF, the data object, and data attribute. And we'll get to see a little bit more of that in action here in a couple moments. Christoph, back over to you.
Thank you, Jackson.
Okay, you should have the screen.
Yep. Okay, so now we have seen how we create a specification. We have seen what we receive from related to the IEDs, and now we can start the process that we do with the system configuration tool, which means import the specification, import the ICD files, and start to do the whole design. When we do a top-down engineering approach, in the first step, we typically can start with the communication engineering. That's similar when we do a conventional approach, when we have our communication drawing, where we have all the devices. And in addition to that, we may have a table with all the addressing information per devices. So it's a similar step that we are doing now, which basically means based on the ICD files that we have imported, we instantiate IEDs, give them unique names. We then link the IEDs to the process part, so what we have specified before, and we design the communication network. So this looks initially like something like this. So we create a communication network, we create subnets, we instantiate IEDs, we provide unique names to these IEDs, and we also give them addressing information, the IP address, but as well as some additional addressing information that we require in the 61850 communication world. In SCL, the communication section that Jackson has briefly mentioned before, that's basically a collection of subnetworks. And under the subnetworks, we have access points that associate basically the IED with the communication subnet. And in the access point, it's also where we find the different kind of addressing information. We also can configure target addresses for the GOOSE and sampled value messages. That's also part that is expressed as part of the communication section in SCL. I also mentioned that we have to assign the logical nodes of the IEDs in the relation to the logical nodes that we initially created during the specification stage, where we had associated logical nodes to the different conducting equipment or to the bay level. Now we can link them to the IED, and as such, we know now which instance of an IED, which logical node within that IED is exactly doing, as an example, the interface to this disconnecting switch, which one is doing the control, so we can with that directly associate what is implemented in a device with where this functionality is located in our one-line diagram. So as part of these steps, what we are basically doing is we import the specification file, the SSD file, which creates us in our STL file the substation section. We import the ICD files, create instances out of them. So as an example, we have 4 bays with 4 bay controllers. They are all identical from the models. So we import the ICD file for the bay controller, create the first instance and the second instance for each of the bay, and give them unique names. And as mentioned at the end, we also configure the communication section, which basically then adds this communication section to our STL file. So again, how does this look in our project? And I have again a little screenshot here. So if we go back to our project now, as an end of this step, we have our system drawing or comms drawing, where we see the different IEDs connected to networks. We have here 1 switch per bay. In a bay, we have the 4 IEDs, starting with the merging unit, the switch control interface, the protection device, and the bay controller, and we have that in all bays. We also have some station level devices like busbar protection, like the merging unit for the measurement bay, the gateway, but then we also added test tools, because it's always a good idea to add the test tools in your design so that they can also get the information that you may need to get for the testing. So that was the communication engineering. And now the next step, that's where we really build our applications, where we create the engineering for the signal flow to implement our protection and control schemes. So what we are doing here, we basically, when we look at an application is typically realized by different functional elements that exchange signals between them. That's a generic concept of an application, independent of 61850. In IEC 61850, the functional elements are the logical nodes, and the information exchange between the logical nodes can either be internal in a device, or it can go across 2 devices. And if it goes across 2 devices, we typically would use the GOOSE service or the sampled value service, which is basically replacing the wires that you would have in an approach without GOOSE messaging. So in a conventional approach, this similar step would mainly be to draw the wire diagram, which shows the wires going between the devices, which basically is the signal flow between the devices. So in 61850, an application could look like what is shown here, which is the breaker failure application. We have a couple of protection logical nodes shown, which would go into the protection trip logic. This would generate a trip that goes through the breaker interface, will trip the breaker. We may also initiate the breaker failure function. The breaker failure function may be what is not shown here, a retrip of the same breaker. If that still fails, it has to trip all the neighbor breakers that can then help to clear the fault, and it does that with the signal rvrf.optex. So this is just the signal flow between the different functional elements, and now depending on how we allocate the devices, and in our case we have chosen devices like this. Now you see some of this signal flow will remain internal to the device. So that's currently out of scope of IEC 61850. Some of the signal flows are now between the devices, and that's where GOOSE comes into the game. So basically now, instead of having a physical output here with a wire going to a physical input, we have now a virtual output with this signal from the 61850 model going in a GOOSE message, and we have here a virtual input that is going then as an initiate breaker failure into the logic node breaker failure. In a similar way, the external signal will go to all the IEDs that interface to the neighbor breakers. That's basically how the application is looking in IEC 61850. In a conventional world, as already mentioned, you would just have wire diagrams showing these wires. In IEC 61850, we can then, in our data model that we have with the IEDs data model, we can now also provide inputs. So as an example here, we can provide inputs to an XCBR, which would be these different op external. And with that, we will now demonstrate that in the Helinx STS tool. Jackson will show you how this configuration is done in the tool.
All right, thank you, Christoph. So as Christoph mentioned, the 61850 engineering process largely revolves around a class of tool known as a system configuration tool, or SCT. One such SCT, which Christoph has already introduced, is Helinx STS, which can be seen on my screen now. So one of the purposes of a good SCT is to provide a layer of abstraction in the engineering process, allowing users to build and interact with their substation applications at a graphical level, and then letting the tool generate the necessary system configuration language, or SCL files, for us in the background. So with that in mind, the screen that you see here is where I've defined the high-level applications that I want my substation to perform. Let's take breaker failure as an example. But to give us some context for how we want our breaker failure application to perform in this specific substation that we're building, let's take a peek briefly back over at the single line diagram that Christoph showed us earlier. So looking at this single line, we see that we have 4 breakers in this substation, or 1 in each of the 4 bays. So I think it's safe to say we could assume that if any one of these breakers were to, say, fail to open, we would want to clear the bus here at the bottom by opening the remaining 3 breakers. So now I know what I wanted to do. Now, how can I configure that? Well, I'm going to head back over to my application schemes page. I'm going to right click on my breaker failure and open the application editor. So here I'm editing the application that I've named breaker failure. And we can see 4 boxes on the left and another group of 4 boxes on the right. The group on the left represents the breaker failure functions for each of the 4 breakers that we just pointed out over on the single line, whereas the group on the right represents the interface units to those same 4 breakers. Another way to think of this would be to say that the boxes on the left represent outputs and that the boxes on the right represent input terminals, where I can draw a line between the two, and I'm sort of making a connection or routing a signal between them. So let's take a look at the box in the top left as an example. Here we see an output named opx.general, which in this case is an output being used to indicate that a breaker failure has occurred. By drawing a line or several lines across the page, I've connected that signal to the trip inputs on the other 3 breakers present on the single line. As Christoph pointed out in his slides, in a sense, what we see here is really not that different from how this might be done in a traditional substation. Although in a traditional substation, we might think of this as a wiring diagram of sorts, with each line representing a distinct copper wire. However, here, each line that I draw coming from the left will tell my system configuration tool, Helix, to configure the devices on the left to publish the associated signal in the form of a GOOSE message. Similarly, every place I connect a line on the right will tell Helix to configure the device on the right to subscribe to that GOOSE message. And if you're new to 61850, this can all seem like a lot to take in. But what we're looking at here is really the crux of the signal engineering portion of the engineering process, which is one of my favorite parts of the engineering process. And I feel like it really encapsulates a lot of what makes 61850 unique. So I do want to take a moment to appreciate what just drawing this line across the screen has accomplished. By taking a signal that traditionally would go over copper and changing it over to a GOOSE message, we've effectively decreased the number of trenches that need to be dug in our substation, the amount of conduit that needs to be buried, the meters of copper wire that need to be run, and the number of terminations that ultimately need to be made out in the field. It's pretty neat when you think about it. But moving on, enough on that, we can now switch over to our communications editor. So here we see what our tool has done for us in the background. By making that connection over in the application editor, the tool has added that data attribute over to a data set in my datasets tab of the application editor. And here we see the opx general signal that we looked at before. It has assigned that data set to a GOOSE control block, which I can see by coming over here to GOOSE control. And again, that same opx.general signal that we routed across. And then up here in that same GOOSE control block, we can see that it's documented the 3 different IEDs that are subscribing to that GOOSE message, all the way down to the logical node within that IED, which is receiving it. So this information that we see here is still in kind of a graphical form within the SCT, but once we generate our SCD file, which is our end goal for using this tool, this information will all be encoded down in SCL. Now, finally, before I move it back over to Christoph, I want to show the GOOSE matrix, which is just as another opportunity to look and see in a graphical way. Okay, here's my GOOSE control block, and then the device that it's being published on, a little bit of a description, and then as I scroll over, these different columns are the different IEDs which are subscribed to it. The percent indicates that this is the publishing device, and then anywhere where I see a yes in that column indicates that other IEDs have subscribed to that given GOOSE message. So with all of this that I've been able to see here in the communications tab, I can now feel comfortable knowing that my system configuration tool has accepted my settings and has encoded them correctly down in the SCD. And I'm now ready to move on to the next step in the engineering process, which is going to be the functional implementation. And for that, I'll turn it back over to Christoph.
Okay, thank you, Jackson, for that little demonstration. So now we are more or less getting to the end of our engineering process. With this, we have to implement what we have defined in the system tool in the different IEDs. So for that, the IED specific tool imports the SCD file, but then we have to do some specific configuration, which is IED specific, which is not yet necessarily standardized. That's why it has to be done on the IED tool. So one of that is the process interface. So we need to configure how the signals that we get from our physical process, like the contacts, the open and close contacts from a breaker, how these are wired in on which binary input we find them so that we can then blend them into the data model of the position. If the IED has a local HMI today, that's also not yet standardized. So how to configure that local HMI is a specific of the IED tool. We may need to configure logic functions. Also, that's something that is now as well available as part of the standard, and we will talk about that briefly a little later. And we may have to configure parameters that are not expressed in the 61850 data model. It's also an area we are currently working on. And then we are more or less ready to deploy the substation. So to summarize again what we have done with the SCL and engineering process. So the SCL allows us to do a formal specification, which is then expressed in the substation section where we have the topology, the electrical topology. We can associate to that functional requirements, signals grouped by the functional elements. At the end, when we added our IEDs with the data model, the communication, at the end, we have basically a machine processable documentation of the 61850 related configuration that is not only used during the original commissioning and design process, but it can also be used for testing. We can use it for simulation, and it can also be used later during the life cycle. And how we can use that for simulation will now be demonstrated by Jackson, where he has a demo now of this project that we have created. Yeah. So Jackson, it's over to you.
All right, thanks, Christoph. So just to reiterate, one of the big benefits of the 61850 engineering process that Christoph's been talking about is that it results in machine readable documentation of the substation. And that is, of course, in the form of the SCD file or substation or system configuration description. As you have seen, if we follow the design principles and best practices being discussed today, it's going to result in an SCD, which essentially contains the 61850 substation's equivalent to a traditional single line diagram in the form of the substation section, a communications drawing in the form of the communications section of the SCD, your SCADA data maps in the form of MMS reports and the associated data sets, and kind of the equivalent of your interconnect wiring, and that's going to be in the form of your GOOSE and sampled value configurations. So the benefits of all of this are pretty numerous, but specifically from a testing and simulation standpoint, having all of that information available in a machine readable format creates some pretty exciting possibilities, which is really what I want to highlight for you next. So let's start with the first thing I mentioned, the substation section. As mentioned, a well-formed substation section can contain all of the information needed to recreate your single line diagram, which is what we've been able to do here. When DTM, our flagship simulation tool, imports the SCD that we configured earlier over in Helix, you're given the option to generate the corresponding one line automatically, which is what you've seen here. There's not a need to redraw it or transfer it in some other way between the two tools. It's all encoded within that SCD. Next, I want to come back to the communications drawing equivalent, which is the communications section file of the SCD. For that, I'll be switching over to Test Suite Pro, our 61850 monitoring and testing tool. By loading an SCD file into Test Suite Pro, we can determine the relevant IP information necessary to establish an MMS connection to the different IEDs in our SCD. And that's without any manual configuration or know-how. There's no need to pull up a comms diagram and zoom in and find out which IED I want to connect to and what its IP address is. I simply load that file in, and contained within it are all of the connection information and IPs needed to connect to those devices. In kind of a similar vein, we have our MMS reports documented in the SCD. So MMS reports are the equivalent of the SCADA data maps that were really the hallmark of legacy SCADA protocols. But instead of needing to exchange and manipulate and import proprietary spreadsheets, now I can just browse to them using the tool. So in this case, I'm using our advanced client. I've chosen one of my IEDs that's within that project, and then I can browse down into LLN0 and then into my report control block section. I can find the data set that's associated with it and just locate it. Now I can see all the data that's going to be available up to both SCADA, or in this case, my testing tool. And finally, that brings me to GOOSE messages. So these are also documented here in the advanced client section. Let's take a look at this GOOSE control block here. And if we expand that out and we look at its data set, then I can see that op general or opx.general that we configured earlier over in DTM. And this, of course, is the breaker failure that's being sent out to other breakers to let them know to open. So GOOSE, just as a refresher, is the high-speed replacement for traditional copper wiring. And by including it in our signal flow in a machine-readable format, our tools like Test Suite Pro can not just show it here in the advanced client, but monitor and visualize that data flow in a variety of different ways. That's really what a lot of what this tool, Test Suite Pro, is about, and it's really inundated the tool. You can view and use those GOOSE messages in a number of different ways. But I think probably the most impressive of those is actually the signal flow diagram, which is what I want to highlight next. So for those of you that might not be familiar with our signal flow diagram, either from using it personally or past webinars, I'll give it a little bit of an introduction. What we see here is an application that I've drawn together showing different IEDs, logical nodes, and the GOOSE messages between them. So in this case, it's our breaker failure application. We see the different IEDs that are a part of this, indicated by the light blue boxes, and you can see their different names up here at the top. Within that are some of the different logical devices that are on those IEDs, and that's indicated by the darker blue. And then finally, the logical nodes, which are the smallest boxes inside. So these lines that we see going between two devices is a GOOSE message that's configured in the SCD. Now, again, by making that machine readable and importing into my tool now knows that there is a trip signal, let's say, going from the PTRC on my D1 line 1 LPU1 device and being passed over into the XCBR logical node on my SCU for that same line. But that's all nice and cool. It's interesting to visualize it, but what's really neat is the fact that we can then capture that information and play it back. So to show you what I mean, I'm going to go ahead and begin a capture. And then using DTM, the tool that we looked at earlier, I'm going to be triggering a breaker failure. Now in this case, it is all on simulated devices, but the tool Test Suite Pro doesn't really know or care that it's happening on a simulation and not as part of a real system. In this case, the tool just simply captures the 61 and 50 communications that are happening on the wire. So again, I'm going to disable a breaker so that it will result in a failure. I'm going to trigger a fault. That breaker will not open because it's failed, but it will send the message out to the other three and open them. Now that'll happen very quickly, but to show you a little bit of what happened, I'm gonna stop it and then step through the different events. So the first thing we see happened was a trip signal, which was sent out from the PTRC as a result of the fault that was detected. And that was passed to two different places. First, and probably most importantly, to the XCBR, which should send an actual copper wire down to the breaker and energize it, tripping a coil, which will actually cause your breaker to open. When that happens, we should see the position value update to the RVRF, who also received that trip signal, and he should say, okay, everything's good. But in this case, because their breaker has failed, it's not going to see that position value change. Now, at the same time that the XCBR received that trip signal, the RVRF also received it, and he began an internal countdown, waiting to see if the position value would change. Now, of course, because it doesn't, we can see that the RVRF sends an op in general, which in this case we're using as a secondary trip, which is being passed up to the XCBR. So just in case the first one didn't work, hopefully this one will. And he's going to go ahead and begin a second timer to wait and see if the position value updates. When it does not, after that timer expires, the RVRF does his job and he sends out his opx.general, which is the signal that we configured earlier over in Helinks, and he's going to send that out to the other three XCBRs or breaker interface logical nodes for the other three breakers in our substation. And as they are not disabled and are not experiencing a failure, they're going to in turn open their 3 associated breakers, which we see reflected here in this pause.opOK value changing to true. Another place that we could look at this would be over in our custom display in our tool, where we do see red, which indicates that our failed breaker is still in fact closed, whereas the other 3 breakers in our substation have swapped to open. So what we saw here is effectively a test that you might perform as part of commissioning of a real substation, and everything went smoothly. But let's say something was to not work correctly and not actually operate as expected. In a traditional substation, that might require a day of walking around the substation with a multimeter, flipping through wiring diagrams for all the different cabinets, opening up panels, and checking interconnect wiring in order to troubleshoot and trace down the problem. But by moving these control signals over to communications, in this case, GOOSE messages, and then documenting those communications in a machine-readable way, we could easily perform, if necessary, the troubleshooting steps to see where this broke down, just by following these lines and seeing where they stopped or where they failed to move forward. And with that, I hope you have a better understanding of not just what the 6150 engineering process entails, as described to us by Christoph, but also what some of the benefits are that it provides and how those benefits translate into testing and simulation specifically. And with that, I'm going to turn it back over to you, Beth.
We are running a little bit tight on time, so I'm going to save the questions and answers for the end. I do see that the questions are coming in and folks are getting answers online, so that's good. Keep sending in those questions. And what we'll do is I want to make sure we get through all the material. In the end, we're happy to stay on and typically stay on for a good 10-15 minutes as you submit questions and we read them live and answer them live. So with that, let's just go ahead and I'll hand it back over to Christoph for his next portion of his presentation.
Okay, thank you, Beth. So as we mentioned in the beginning, we now will briefly give a preview of some of the improvements that we are currently working on in the standardization community to improve the specification process. This is mainly driven by utilities that have some very distinct perspective for an improved specification, with basically the overall goal to be able in the future to completely submit specifications for projects they want to realize in a machine processable way. So here we see a list of some of the ideas or desires that utilities want, and I will focus on the 2 highlighted ones, what we are currently doing with regard to those in the standard. So maximize testing possibilities at specification stage and reusability. That are 2 aspects we are currently working on. And here we see a view of the top-down engineering process as it is a vision of a utility. We already discussed a little bit before. We start with specification, define the ICD files from the IED tools, do our system configuration, and then we configure the process. And at those stages, we can basically verify with simulation the behavior, but of course in this stage when you have the real devices, we can also do the system testing. As part of the maximizing testing at earlier stage, we are currently working on enhancements that allow us to do as well a simulation already of the specification. And as part of the improvement of the reusability, we are working on defining as well the templating. So before you really start the project, most utilities, they have standard designs that they have to apply. So they, from a utility perspective with SCL in the future, we should also be able to support these standard designs. And one of that is the basic application profile, where we can as well express that in a machine processable way using SCL and then simulate as well with the testing. So basically for that, we talked before that once we have configured the devices and configure our GOOSE messages, we have what we call an external reference to document the signal flow between the devices. What we are adding currently to 6150 is that already at the specification stage, when we define our logical nodes that we require for our functionality, that already at that stage we can implement or define what we call now a source ref, which basically explains how the different logical nodes or functional elements should interact. And this allows then to test the schema already at specification phase before we have configured any configuration, communication, and before we have allocated any IEDs. A second aspect, and that goes into the reusability, is that we extend the process with some new variants of SCL files, which are mainly in the template area. So like a function specification description, basic application profile. So this is new template files that we can then import before we start the specification. So a specification tool will be able to import them. And as part of that, we also add the feature to describe functional behavior optionally using a standardized language like 61131, which is function block structured text. So this allows us to describe and specify certain behavior as well in a standardized way. And that's what now will be shown as the last demo by Jackson, how we can apply 61131 for behavior description and simulation then with the appropriate tools.
Thank you, Christoph. So as Christoph mentioned, this section of the webinar is really all about highlighting some of the upcoming changes and additions to the IEC 61850 standard. As such, some of these new features are really still in the process of being integrated into our tools, but once those additions to the standard are finalized and tool support is finished, which we're targeting for maybe into the summer, rest assured that we will have a follow-on webinar series where we really do a deep dive into what is made possible by these enhancements to the specification stage of the engineering process. But for now, I just want to give you a preview of what support for 61131 structured text and function block diagrams will look like. And with that, I'd like to introduce the 61131 module within DTM, which is what you see up on my screen now. So for those of you that might not be familiar, 61131, specifically -3, is a family of programming languages typically used by programmable controllers. It's commonly associated with PLCs. So if you're familiar with ladder logic, structured text, or function block diagrams, those all are defined as part of the 61131 family. And DTM 2.0 will include support for importing, editing, exporting, and most importantly, running or executing both structured text and function block diagrams. So aside from just providing users of DTM with another method to script behaviors and tests, in addition to the JavaScript support that's already included, this will allow for functional behaviors, a part of the enhanced specification stage, to be imported and simulated directly here in the tool. So what does that really mean? Well, currently, when you want to build a simulation here in DTM, we handled the one portion of it for you completely, and that's the communication side of things. But when it comes down to behavior, if you want it to be done out of the box, a couple, let's say, assumptions have to be made. That is no longer the case. If you can now define the functional behavior of your device in 61131, and we can now simulate that exact behavior, this allows for more accurate simulations, and that's with a lot less manual configuration. So with that, let's walk through what a function block diagram looks like. In this case, you'll see that we've associated function blocks with specific logical nodes. And if these don't look like the logical nodes that you're used to, this demo application that we put together is for a DER application, specifically battery systems. But there's no specific rules defined as to how you need to use these function blocks. Do they need to be associated with a logical node, or can you just write your logic however you like with ands and ors and counters and the other building blocks that are part of the 61131 standard? But in this case, that is what we've done. So in some ways, it looks a little bit similar to what we saw over in Test3 Pro with our signal flow diagram, with signals flowing from one logical node to another. But at this specification stage, we've not yet associated these logical nodes with IEDs. So these may end up being a GOOSE message should these two logical nodes one day exist on different devices, but it's also possible that this will all be logic internal to a single device. which brings me to source refs. So source refs also allow you to do things like this: specify connections between two logical devices before you really get to the communication side of things. You don't need to know or care whether or not these logical nodes will exist on different devices to specify a flow of data between them. Now, this is just a device where we can, a function block where we can see inputs coming in and coming out. I do want to point out that we've implemented the behavior of this function block using structured text. And to do that, I'll come over here to my DPMC and I'll just edit the structured text. And you can just get an idea of what structured text looks like. It's maybe a little bit C-like. You can see I've defined my inputs and outputs up here at the top, and then I have some logic down here defining what will happen to my outputs based on my given inputs. And then I can instantiate this function block multiple times if necessary, or add it to a library and use it in other projects over here in my function block diagram. So with that, in summary, I just want to say that the upcoming additions to the 61850 standard are really going to enhance the specification stage, and specifically the 61131 support combined with source refs are going to allow for more complete simulations at an even earlier stage in the engineering process, specifically the specification stage, than ever before. And with that, I'm going to turn it back over to you, Beth, where we will be doing question and answers. Thank you so much for sticking around.
Okay, thanks, Jackson. Yep, so we are just at time. So what I'd like to do real quick is just wrap up and go over some details, and then I will switch over to questions and answers. We've had a lot of good multi-questions from one person come in, so a lot of detailed answers going back out. Before we get back to that, I do want to just mention that the webinar will be posted to our website probably within the next couple of days. And again, right now, if you go to our homepage, you will see part 1 there right front and center, so you can go look at that at any time. When you do log off of here, you will be prompted for a survey. It's only 5 questions, takes less than 2 minutes. Really appreciate if you fill it out and give us any feedback that you have on the webinar itself, any future ideas of what you'd like to see in webinars. So we really appreciate any feedback that you can provide. Also want to point out, you can sign up at any time for part 3. That focus of that webinar is strategies for integration of DNP3 and IEC 61850. That will be hosted on May 24th at 10 a.m. So again, you can go to the website now and sign up for that and get it on your calendar. And of course, if you have any questions at any time, please feel free to email sales@trianglemicworks.com. So with that, I would like to go over to the questions and answers for anyone that would like to stay on longer. And I think I'll just kind of take it from the bottom. We've had, like I said, quite a few lengthy questions come in. So the first one, and I believe this one will be for you, Christoph. In our substations, we don't have complete SEL files. Is it possible that any tools in Triangle to get SEL files effortlessly, and then we make all the ICDs that we already collect into SCD files with Triangle software?
Okay, thanks, Beth, for the question. I think it really depends. When you say you don't have complete SCL file, it depends a little bit on what is missing. I mean, we certainly can import an SCL file as an example in the Helix STS tool that we have demonstrated, and we probably would need to do some reverse engineering. As an example, if the substation section is completely missing, so the complete one-line diagram is missing, that would need to be reverse engineered. So there is some work involved in that. So it's not necessarily possible to do that on a push button. But yeah, so it really depends a little bit on what does not complete SCL file mean.
Okay. Next question, I believe this will be for you as well, Christoph, and certainly anyone, any of the engineers that have been answering the questions behind the scene, you may feel free to speak up as well. So I'll just read it. I have a question regarding the creation of the CID file. How would it be constructed? What elements of the IEC 62050 do you need to be included?
Okay, so the CID file, And there was a similar question related to that I probably also just answered. The question was, can we import a CID file in the process as well, other than just an IID and an ICD file? So the difference between an IID file and a CID file is an IID file just describes the instance of the device with all the data model, all the configured values of parameters and the configured communication. The CID file is intended for the IED that we configure to have everything in it needs. So besides the information what we have already in the IID file, which is everything related to the IED under consideration, we need to add information like communication addressing. So there will be elements of the communication section in that file because the device needs to know its IP addresses. But if the device is publishing or subscribing GOOSE, so if it's publishing GOOSE, it will also find in the communication section the communication parameters for the GOOSE message it has to be publishing. And if it's subscribing GOOSE, in addition to having the communication parameters of the GOOSE subscription, it also needs to know the structure of the GOOSE message. And for that, the CID file needs to have additional extracts, at least from the IEDs that are publishing the GOOSE messages that it has to receive, because that's where it finds the data set and as such how the GOOSE message is structured. I hope that clarified.
Okay. There is a follow-up question to that, but I think we might need some additional information. So maybe you could just, I'll read the question, Christoph, and ask if you do need additional information to answer it. Is there any way to merge two CIDs if there is two collateral substations that need to speak with each other?
So that was for me as well?
Yes, it's a follow-up to the first question. He has two in a row.
Yeah, I'm not really clear what is meant there. I mean, the CID file describes one IED. As I just discussed, it describes the IED and what it has to subscribe to. There is a process of getting information from two substations where the devices have to communicate with each other. There's a process defined in SCL through what we call an SCD or System Exchange Description file. But that's basically exporting from one project the information related to an IED that I have to subscribe on the other side. And then the project for the other side would add this device into its project and be able then to subscribe as well to messages from there. So in some way, yes, that's merged, whether it's done on a CID basis or rather on an extract from an SCD file, that's depends a little bit on the implementation, but yeah, in principle, it's possible through the tools to, I wouldn't really call it merging it, but to include in the other part the source device, which is from the other substation.
Okay, thanks, Christoph. I believe another one for you. How in GOOSE message communication is the failsafe maintained for communication failure with the subscriber IEDs?
That's as well for me, I guess.
Yes, that's for you, Christoph.
Okay. Okay, so the GOOSE mechanism has, the GOOSE messaging in 6150 has some mechanisms built in that help to deal with that. As you probably know, GOOSE is sent out as a multicast. So it's more or less sent out over the network. We don't get an acknowledgement of reception from the subscribers because that would anyway not be helpful from a timing perspective. But the GOOSE mechanism has on one side a repetition built in. So when there is an event happening and a new GOOSE message is sent out, that message will be repeated. So if you have a communication disturbance at a certain moment, the repeated message should get to the subscriber. On the other side, it's the responsibility of the subscriber to be sure that he gets the latest information. So with this repetition mechanism, we also have a built-in supervision mechanism. So the subscriber knows if the publisher is not publishing anymore. And as such, he then needs to behave accordingly in a similar way like he would not get a physical input. He needs to behave in a fail-safe behavior, but he definitely can know when the source is not there anymore and does not publish. And then it's the responsibility, and it depends, of course, on the signal. When you expect a trip there, you just don't do anything. When you expect sampled values, you may need to block your protection function. So it's the subscriber, depending on the signal, that needs to behave in a fail-safe way. But he definitely will know if the publisher is dead.
Great, thanks, Christoph. Jackson, I believe this one is for you. Can we simulate the IEC 6150 server and client using TNW software, and which software will be used for which application?
Absolutely, yeah. So you can actually accomplish that with both DTM and Test Suite Pro, depending on what your goals are. If you want to simulate behavior of your device, that's firmly a DTM application. So for that, you would need some sort of SCL file, maybe an SCD or an ICD, and you could import that into the tool and use it to spin up a server and a client as well that would connect to it. And then using scripting, I mentioned in brief that JavaScript is supported. There's a variety of other ways to interact and control your simulated devices. If you simply want to bring up a simulated server and interact with it, let's say manually by clicking and changing values in the advanced client, or I guess the equivalent, which would be the server simulation data model, then you can do that in Test Suite Pro as well. And if you want to reach out afterwards to our sales and support team, we can help you pick out which tool is going to be best for your specific need.
Thanks, Jackson. Okay, next question. I believe this will be for you, Christoph. Different ICD template files can have different data type definitions. How do I make sure all the data type definitions from different ICD template files are unique in the SCD file?
Well, in principle, that could be a question for Andy as well. That's the system tool that needs to handle that. So when the system tool imports a new IED, can be an ICD file or an IID, it needs to be sure that the names of that is unique. If not, it needs to modify it. It can modify the names. But at the end, it's the tool that is combining them that has to make them unique. A good praxis, however, would be that vendors in their data type templates fill in as well the IED type, because that's an optional field, and that would make it easier to keep it unique. But it's the tool that combines different IEDs that is responsible to keep them unique.
Yeah, maybe to add to that, so Healing's SKS will distinguish those data type definitions for you as you import them, and ensures that they're always consistent and unique by appending a unique identifier to it. And then when you export an SCD, you can be sure that there's no weird type collisions going on. And I don't know how other tools do it. It's just STS does it like that.
Great, thanks, Andy. Thanks, Christoph. I have another question. I'll just throw it out to whoever the best person is to answer this. So if I understand correctly, some LNs may have behaviors dependent on the manufacturers.
Yes. So I think one way to think about it would be an LN is a collection of data attributes, uses 6150 term, variables, points, whatever you want to think of them as, associated with a specific function. So we talked about that breaker failure function earlier. So how a breaker failure function works from manufacturer to manufacturer probably isn't that different, but it could be. But the assumption is that they want to use a similar set of data attributes between them, and they can customize that a little bit in the data template section. There's some required and some not. But as you get into, let's say, protection algorithms specifically, that really could vary from manufacturer to manufacturer. They might have a different algorithm for a differential protection if you go to SEL versus if you go to ABB.
Great, thanks, Jackson.
Mm-hmm.
So I think that wraps up our Q&A session. There's a couple other questions that have come in that we will review, and in the follow-up, I will send out the full question and answer document. So you will get access to that as well. I appreciate everyone's time and staying on with us a little bit past the hour as well. And we hope to see you at our next webinar on May 24th for part 3. Thanks, everyone.
Thanks.